work with WT Smith, so we are actually investigating the boundary conditions in a twisted transfer model series known as the ADJM and BRG model. So we are considering the M2 branes wrapped on Riemann surface and twisted on a Riemann surface. And then the geometry of M series is taken as case equals R7, and such a Riemann surface is embedded in this case 3. And this particular configuration actually preserves the H supercharges on the volume of 2 branes. And then we first of all consider the boundary condition of this series corresponding to the non-parallel M5 branes attached on this M2 branes. So these non-parallel M5 brane actually fixes the propagation of the M2 brane in the first phase. So still, so they can move in just a normal bundle over the Riemann surface inside the case surface. And actually we found that boundary condition, some combination of boundary condition as a superset boundary condition and gauging by boundary condition as a unified boundary condition of a complexified gauge fields. And then also after twisting, so that we have some different type of the fermions, known as the symplectic fermion, with a spin 1 and spin 0. So all of such as a resultant twisted theory with particular boundary condition. So we can actually summarize the total action as the supergroup based on Richter model. And so particularly if you think of the UN ABJR model, and if you twist this series, and then consider boundary condition, we can get the supergroup N/N BW model. So then the problem is, what can we learn from this series? So in this talk, I will propose the partition function of indices of this series, and we put the theory on a torus, and then the torus. So if you study parameterization with series symmetry as a modular group SO2Z, so this partition function or indices actually reflected this symmetry. So SL2Z is a very important symmetry. So in a string theory and black hole physics, and also the mathematics. So let me give you the example. So the simple example is a modular form, which is a homomorphic function on upper plane. And the modularity is actually ensured for the just partial integral formulation of the partition function. And the simplest example will be the partition function of the chiral boson, a bosonic string. So in a trace formalism, we can write down this form, and then the resultant quantity is written as the in terms of just a modular discriminant delta. So you might think this is not so interesting, but if you think about this formalism as a trace using the Hamiltonian, so we can write this function as a Q series. Then you can extract many interesting features, properties from the Fourier coefficients. So I advocate here string theory, black hole physics, and mathematics. So we can extract the information of the number of the so known as some double Harvey states. That is the solitonic string theory states. And also this dn is the number of the microstates of the 4-dimensional n equals 2 black hole, and with the relation of the n to the just electric and magnetic charges. And also in mathematics, so you can think of this number as just a parallel partition of the n integers with 24 parallels. But more interestingly, the Zaslow and Yo proposed this is nothing but the number of the rational n+1 nodal curves in K3. So this is known as the Yo-Zaslow conjecture. And also the other example, so we can think of the Jacobi form. This is just a homomorphic function on the upper half plane and close just a complex plane. And they have the modular property, and also under the translation of the complex plane, we have the ellipticity of this function. The example is so known as just genus, the two-dimensional n equal 2, 2 SGFT is the model description for the target space M. So the definition of this function is given by this form. And so as we can actually show, so this is known as elliptic genus in mathematics. So this is the capital valued invariant, topological invariant of the elliptic such a generalized homological theory.
Sorry, the black hole you mentioned is actually part of this black hole of n equal 4 theory?
Here?
Yes, in the previous slide.
Previous slide is yes, the book how it states. It's the 8 supercharges. So the 8
by n equal
supercharges.
2, you mean 8 supercharged black hole?
Yeah, the 4, 4, I think, the case. Because that's the case with only we have just a quantum number n. But here we have additional angular momentum. So as I show you here, this is the other example.
So this is 4 supercharged black hole in n equal 4 theory.
Yeah, here it is. So this case, we can also think of Q series expansion. Then this number is, so one interpretation is string theory. So this is a bound state of the D1, D5 frames with charges Q1, Q5 with this relation. So this actually the partition function. Actually we take the target space as a symmetric product of the K3 surface. So the other one in black hole physics, as I saw, so the theory before that, just a 4-dimensional equal 2. Here, so we have 5D black holes with just angular momentum in the 5D. And also, we have the relation for M with just electric charges of the black hole. So this is known as Strominger buffer black hole. So going back to our problem, so we are interested in the computation of this index. So this definition is almost same as elliptic genus. But I would like to explain what are the definition of these operators, these indices, and also I show you that this encoding the information of the brain system. So the remaining talk, I will talk about some data of these indices as brain computations, and also method to compute these indices, and also the properties of these indices using particular results. Okay, so let's start with analysis of the superaggressive novelty model. So the action is given by this form, and also this action is invariant under the semi-local symmetry. So omega z and omega inverse, omega bar inverse d bar. So they are actually the product transformation of just left multiplication and right multiplication. And then we can actually derive the current of this. And then the current actually satisfying the current algebras. So you can actually think of the infinitesimal transformation of this current and insert it in the word identity. Then you can find these algebras. So this is known as the affine Lie algebras. But here we are thinking of the Lie superalgebras. So this is just a more general case of the affine Lie superalgebra. So in order to study this theory, so we have to understand the representation theory a little bit affine Lie super case. So Lie superalgebra has been written with particular the sum of the loop algebra and also central extension and derivation of the corresponding to this variable t. And the commutator and the bilinear format is like this, and AB are just superalgebra values, and MN is just integers, and we can take the Cartan as this form. So this is just H is the Cartan of the finite Lie superalgebra. And the coordinates we can pick up H. So we are taking the tau t as the complex numbers, and Z as just a Cartan element of the finite Lie superalgebra. And in the zero space, we can take root space, and we can pick up the basis of the system of just the finite Lie superalgebra fraction and delta with some interval. So actually, I noted by so actually I'm considering here the GL n slash m Lie superalgebra. So we have the indices 1 to n and 1 to m, and in this particular bilinear form relation, and we can pick up the weight using this basis. So K is just correspond to the just level just omega 0, omega naught. And lambda is just the element of the Cartan in the finite superalgebra, and n is just a number, just a quantum number of the just a derivation of this d. So then we can think of highest weight representation of the algebras. So this is a well-known just affine Lie algebra. But a new feature actually coming from the just the existence of this particular loop. So this is known as the isotropic loop. So they are actually commuting with each other. No, sorry, this is kind of a so the vanishing condition for this bilinear form. So this is the element of the element of the odd root in a Lie superalgebra. So the number of this beta satisfying this actually was also orthogonal to the highest weight. And this number is known, so called as atypicality in mathematics. And actually, so I will propose to, so the mechanical root analysis, they are actually proposing the meaning of atypicality in using the different configuration as I showed you before. And also I will show you what is the meaning of this in just our brain configuration. And using basis, we can write down just the highest weight in terms of just the xi, yk, just integer values for the quantum numbers associated to the just affine Lie superalgebra, affine Lie superalgebras. And if you fix this weight, so we can actually consider some particular highest representation. And mathematics actually introducing some combinatoric weight, so the tool as a weight diagram. So using this weight diagram, so actually we can think of some chapter formula, improvement of chapter formula of the affine Lie superalgebra. And also, affine Lie superalgebra has not been done, but actually can be analyzed by using weight diagram, in particular some combinatoric algorithm. So I will show you briefly the weight diagram what it is. So weight diagram is consists of just 4 signatures and also horizontal number line. So this is the integer horizontal number line. So then we put these signatures by following these procedure rules. So for instance, we can actually put these signatures on a number line. Then we can actually leave these signatures and also the left open and right open. And then we can write down the weight of this particular weight diagram. So they are just 1-to-1. So this is example. So we can actually check the correspondence. So similarly, so now so we are actually thinking of some particular brain configurations. So in brain configuration in our analysis on our construction, so I have 2 brains actually wrapping Riemann circles. And then so in this M theory we have C fields, the C form gauge fields. And then actually this basis, alpha is just a 2-plane basis. Then so we can actually extract the M2 brain charges under the charges of this U1 gauge fields. But also we have the M prime and F prime plane. So these charges actually separated into there is the xi and yk here. So this is a schematic picture. So we have this particular configuration of M2 brains at the middle. This is the intersecting just like M5 into M5 prime. And then also we have some additional M2 brains ending on just one of the M5 brains. Then we can assign the numbers, the quantum numbers, the charges of these like this. So we can actually associate these quantum numbers with the signatures of the weight diagram. Then we can actually assign the weight, just highest weight of the state in the following. Then so at this stage we can see that atypicality is just these signatures corresponding to the number of stretched M2 brains with M5. So so I couldn't show you, but actually so atypical just root is corresponding to just the same number of the charges. So if we have just the same numbers for the xi and yk, then we can understand these roots just associated with the atypical root. So this is the data of the indices. So now so we understand this H is just atypical. This H is the Hilbert space of the series, but this we are taking this Hilbert space as the atypical module with atypicality being stretched the number of stretched M2 brains. and F is just a Fermi operator, Fermi number operator, and L naught is just a Hamiltonian. And that will be Hamiltonian is taken as just a this energy of X with M2 corresponds to the winding number around the time cycle of the stage M2 X. Then FA is the generator, is taken as just charges, as I showed you the M2 charges. So if we compute these indices, so we expect to get the number of such a generating function of the degeneracy of the BPS states consists of the M2 and F5. So the method to compute is just working model formula, but I have not so much time, 10 minutes. So recently, the mathematicians actually proposed a very interesting formula known as the Katsubaki model formula for the computation of the captives. So I will skip those the derivation, but actually this is the formulas, and then so we can actually derive the some index formula using the Katsubaki model formula. But interesting is to happen because this is not modular form. As you know, the affine algebra case, so the use of ordinary algebra, so we have just a modular form for the character formula. But this affine algebra, this superalgebra character is not modular, but it's mock modular. So what does mock modularity means? So, okay, so maybe there's also plenty of time. So actually, I will briefly some interesting things. So mock modular form is just a homomorphic function on the above plane, and it is not modular, but by adding the non-homomorphic is known as the shadow. But actually, if it performs some integral operation known as the Oikida integral, then we can get a modular form, but it is a non-homomorphic object. So this is actually, so the analysis actually improved by the Vegas mathematician recently. So using the concerning such things, so we can actually think of Modular partition function for the distributed model. So usual case we have holomorphic modular form due to those facts. So we have holomorphic Hilbert space and diffuse spectrum and the supersymmetry. We can compute this as a holomorphic modular form. But on the other hand, in the case of supergroup model, the Hilbert space is not to be the factorized as a holomorphic. So in the anti-homomorphic parts. So it is this atypical sector. So we're proposing that this particular function, I, if we take this as such a modular completion, then we can compute the non-homomorphic part or the modular total partition function. Okay. So here are our results. So for the PSL2 case, and then so this is known as the upper least sum, very interesting function, but I cannot explain it today. But yeah, we are getting such a multivariable upper least sum with order 2 of index 1. And we actually perform the modular completion of this function. And then, so, yeah, maybe, sorry. So, but actually, I have run out of time. So, but this is actually associated with word processing to count such a degeneracy or numbers in some context of the, as you said, degeneracy, so some counting of the curves. The Fourier quotient is very important thing. But this Fourier quotient cannot be determined uniquely for this upper least sum and this particular associated function. So, okay, maybe finally, I will show you some interesting function for the counting the partition function of the polar BPS diodes in just a type 2 string theory on a K3 cross elliptic curve. So that this partition function actually written as we can actually expand this as a meromorphic Jacobi form of weight 2. But this is actually using this mathematical theorem. We can actually like this as a two pieces, finite part and polar parts. And the final part is associated with the immortal black hole. This is stable. But if you think of this particular polar parts, so they include this upper least sum of weight 2. So in our case, we are expecting that this particular upper least sum of order 2 is kind of a generalization. In that we have some multivariable case. So we are now interested in some analysis of the M2 time system. Image string theory, gauge theory, and mathematics. Thank you very much.
Quick question for Tadasi.
Is M2 and 5 the brain configuration for ABGN? Do you know?
Yeah, so the ABGM is just a description of the M2 brain incorporating the flat space, or some before the space. But if
So
you're not thinking of Van conditions in the flat case?
No, so my question is this counting of states is associated to some black hole living when this black hole is living.
Yes, but actually I do not know what type of black hole can arise. But actually we can expect that the CD n equal to supergravity can occur after the convolution of the series in a M-theoretical occurrence. Because this is associated with K3 plus T2 plus T2, then it might be. But actually we have no good understanding for that.
Cool.
But I mean, actually, you know eventually what the black hole is. I mean, what is the supersymmetry of space-time and what is supersymmetry of black hole you are looking at?
So the supersymmetry, remaining this, we have the topological traces theories, but essentially we have two supercharges. So the remaining,
for the black hole.
Yes, and
But
also
what about space-time theory?
Same. The number of supersymmetry will be same, but actually the dimension of the supergravity depending on the some convolution. But we are expecting CD n equal to 2, and then we have some particular half EPS solutions for that.
I don't quite understand what the statement is. I mean, for example, if you have a 4 supercharged black hole in 4 dimensions, depending on whether it is black hole of n equal 2 theory, n equal 4 theory, n equal 8 theory, you have very different behavior in terms of wire crossing, degeneracy, and all that. So this number of space-time supersymmetry is as important as number of supersymmetry of the black hole itself.
Yes.
So I was asking in that context, are you still saying same supercharged space-time and black hole?
So I do not understand what type of solution can actually be associated to this particular brain system.
But
So maybe the M2 M5 M5 prime system, so even in a flat space.
so I mean, other than this, the brains, you don't break any of the supersymmetry.
So K3 surface actually break down this half.
I
So
see.
we have
So
16.
it's a 16 supercharged system.
Yes.
So it
So-
will be like 1/8 or 1/16. Yes, that makes sense.
Yeah. So the things is that we have break half this case, and the additional M2 M5 break just 1/8. Then totally we have 1/16.